ahead and start. Can people on Zoom hear us? Is the audio okay?
Yes, we can.
Yes, okay, great. So welcome. This is the Parallel 2 session, so hopefully everyone is in the right place. The usual announcements, please join Slack and ask your questions there. And one announcement is that our second speaker today had to cancel. So from the third talk on, we're moving them all up a block. Yeah, and for the speakers, I'll give, if you're in person, I'll give you a heads up at when you have 2 minutes left. And if you're not here in Melbourne, I will ping you on Zoom when you have 2 minutes left. And just a reminder that the first student question gets a $25 prize, I think it is. So be sure to ask a question. Okay, and our first speaker we'll be talking about populations of properties of compact objects from the second gravitational catalog. We have Shanika Galaudage. So take it away. Thank you.
Thanks. Hi, everyone. My name is Shanika. I'm a PhD student at Monash University. I'm also a member of OzGrav and the LIGO collaboration. And today I'll be talking to you about the population properties of compact objects from the second gravitational wave transient catalogue, GW190521. So let's move right along. So going back in time a little bit, from the end of the second observing run, GW190521, we had 11 compact binaries. So in blue, we have here the events that LIGO and Virgo detected, and the black holes at least, and then the purple represents the black hole seen in electromagnetic observations. Yellow, we see the electromagnetic neutron star observations, and the orange represents the LIGO Virgo neutron stars. And so this was the result that we had at the end of GW190521. Fast forward to late last year, we have the blue region has completely exploded, which is pretty cool. We have 50 compact binaries now. We actually have 52 now, thanks to the recent neutron star black hole mergers that were announced, and you can hear more about that tomorrow during Hannah and Rory's talk. But today I'll just be focusing on this catalogue. So the second gravitational wave transient catalogue includes observing run 1, 2, and the first half of O3A. There's a total of 50 compact binaries, 47 of which are confident detections. 44 of those 47 are binary black holes, and we have 2 binary neutron stars and 1 event that might be a binary black hole or a neutron star black hole. And so with our population analyses, we explore several different mass, spin, and redshift models, and these models are extensions of the ones used in GW190521. And these models that we use are motivated by astrophysical predictions, and I'll go through a few of those examples in a moment. But the models that, so the models that we use are based on these predictions, but we also have, so for this talk, I'll be talking about mass first and then moving on to spin. And I encourage you to look at this archive link for more because I won't be able to go through all of it today. So let's start with some astrophysics. So on the left here, I have the pair instability process outlined. So here you have stars that are really, really massive, they're greater than 130 solar masses at 0 age main sequence. And these stars are massive enough that well, in the core, the photons are the ones giving the pressure outwards in the core, and these photons can spontaneously become positron-electron pairs, and this decreases the pressure in the core. And this continuously happens, and there's a runaway effect essentially until the core is so hot that it ignites oxygen, and then we have explosion. So in this case, we have no remnant left behind, so the star completely blows up. Moving on to the right-hand side, we have pulsational pair instability. And so in this case, you have stars ranging from 80 to 130 solar masses, and these undergo a very similar process. However, instead of the star completely blowing up, you have it shedding mass, and this process can repeat until the stars get to a mass below around 80 solar masses, and then they can undergo a core collapse supernova and produce a black hole. So the key thing here is, in the first case with pure instability, you have these massive stars not producing black holes. In the second case, you have a range of stars or range of mass stars collapsing down to form similar mass black holes. So what would this look like in our mass distribution? So here I have a cartoon of a mass distribution. And so with pure instability, we would perhaps expect a cutoff at the upper mass of the distribution. And from pulsational pure instability, you might expect a pileup of black holes ranging from 35 to 45 solar masses. So these are things that we can look for in our population analyses. So that's just two examples of some of the things that we look for. I'm going to go through the results from the publication. So here are 4 mass models that we looked at. And these are mass distributions. The solid lines represent the mean of the distribution. The shaded regions represent the 90% credible interval. And so the first model, the truncated model, is a power law distribution with sharp cutoffs at either end. Power law peak is also a power law, but instead of a sharp cutoff at the lower mass end, it has a smooth turn on. And it also has this peak motivated by pulsational pair instability supernova. We also have broken power law, which is similar to power law peak, but instead of a peak-like structure, we look for a break-like structure. So this is when you have 2 power laws meeting and they have a break because they have 2 different slopes. And finally, we have multi-peak, which is kind of in the name. It has multiple peaks. It's similar to power law peak, except it has an additional high mass peak. And this high mass peak is motivated by hierarchical mergers. So these are black holes that have been produced from the mergers of other black holes rather than from stellar collapse. So we also look for that as well. So what do we find? The truncated model is significantly disfavored. So meaning that we see structure in our mass distribution. And it's no longer can be explained by a simple power law and sharp cutoffs. So zooming in a bit more onto this detail from the mass distribution. So on the left, I have a plot of the fraction of binaries that you find in the peak for the power law peak model. So this is the model with a power law and a peak. And so the fraction of binaries in that peak versus the power law component is around 8 to 9%. And so because this distribution is peaking away from 0, and if we were to zoom into that corner at 0, you would see no support for 0. The fact that it peaks away suggests that we do have this peak-like structure, which is interesting. Moving to the right plot, this is from the broken power law mass model. And here is plotted the distributions for the 2 slopes in our broken power law. And the dashed line represents where the slopes are equal. So here, you can see the green distribution is away from this dashed line or excludes the dashed line, which indicates to us that indeed these 2 slopes are 2 different slopes. They're not the same slope. If they were the same, we would just have a power law back, a single power law back. So what we're seeing from both of these models, our preferred models, is that there is structure in the mass distribution, and we can expect, hopefully, with more and more events, to be able to distinguish between these different models. So that's enough about mass. Let's move on to spin. So here we have a binary system, binary black hole system, and the arrow in the middle represents the orbital angular momentum. The yellow arrows represent the spin vectors. The theta values represent the angle of misalignment with respect to the orbital angular momentum. And I've also highlighted in purple the in-plane spin. So by studying the spin distributions, we can learn more about the evolution and formation mechanisms of these binaries. And the in-plane spin component can tell us a lot, specifically in relation to precession. So if your spins are not perfectly aligned with the orbital angular momentum, it means that you have in-plane spin components. So looking at this little diagram that's showing the cosine of the tilt angle, ranging from -1 to 1. 1 represents perfect alignment, -1, perfect misalignment. And if you have any kind of value in between, you would have in-plane spin components. So if you had perfect alignment, it would look like a delta function in this particular plot. So instead of a truncated peak like the orange curve, you'd have a really sharp peak at 1. And so we look for this. We look for the fraction of binaries in this peak and the shape of the peak. So looking at the plot on the right, this is the default spin model. And here we have the fraction of binary black holes in that peak, as well as the width of the peak. And you'll find that the region that I pointed to with 0 width and the fraction being 1 means all of your binaries are perfectly aligned. And we can see that the orange distribution is excluding that region, which seems to suggest that we do have support for having in-plane spin components and thus support for spin-induced precession. So this was one of the highlights from these results. And I'll point out that the broadness of this peak that we see can relate back to supernova physics, where you have the binaries, you have them typically aligned in isolated binary evolution. And if you have supernova kicks, they can misalign it. And the amount that it misaligns can be modeled by how broad that peak is. So to summarize really quickly, with a growing catalog of gravitational wave events, we can probe the stellar evolution and formation mechanisms of these compact binaries with these population studies. And we find that the features in the mass distribution cannot be explained just by a simple power law and sharp cutoffs. We do have evidence for spin-induced precession and more in this publication. So I highly encourage you to go look at this archive link and look at these results. And I will say, stay tuned for O3B. That brings me to the conclusion of the science. I just want to do a few quick plugs. If you've heard of the Includer movement, well, now you have. This is a movement to improve the representation of women in school curricula in Australia. This was started by Kat Ross. So we're always looking for volunteers to help us out in this movement. So please feel free to reach out to Kat, myself, Isabel, and a few others at this conference who are part of this movement. And finally, a plug for Space Australia. We love bringing you space news. So if you have research that's exciting, because we all think it's exciting, please reach out to us. We'd love to hear about it. So if you want to capture these social links, take a picture now. And that's it. Thank you.
Thank you for that very nice talk. We have a couple of questions in Slack. First one is from Reinhold, who I think that means he wins the prize too. Why would hierarchical mergers lead to a third peak? Is that just a consequence of merging things in the PPISN peak?
So going back to the red distribution, so do you mean by third peak meaning, are you considering the low mass end of this distribution? Yeah, so the multi-peak, so the far right one, we're not really modeling 3 peaks. It's just that the distribution, when you've counted for selection effects, that first end far left, oh my goodness, far left is not really a peak we're modeling, it just comes out of it. Whereas the multi-peak and the hierarchical mergers, we expect it to be larger than the pulsational pair instability peak, which is around that gray shaded region in that plot. So we model it to be higher and in fact, sort of double the pulsational pair instability peak. So that larger peak is just meant to be beyond this pair instability potential cutoff. Hopefully that makes sense.
We have another question from Colin Howlett. So thanks for mentioning stock. Thank you. Do you fit the mass ratio at the same time as the M1 distribution? And what does GWTC2 tell us about this? And how does it change with different M1 models?
Great question. So we do fit for the mass ratio model as well. Currently, we just fit a power law and we don't change that mass ratio model. And these results, all of the mass ratio models for these particular mass models were also just simple power laws. I guess we can, there was another analysis in this publication that looked at different kind of populations relating mass and spin. I guess it's a bit off track, but to answer your question, the we only use a power law for all mass ratio models. It might be interesting to look at this further with complicated models of understanding if there are different populations with different mass ratios that are quite distinct. But at the moment, no, this particular publication, we only looked at a power law model for mass ratio for all of them.
And then the last question from Gary DaCosta. How many extra detections are needed to distinguish between broken power law and power plus peak models?
That is a very good question that I probably should.
I'll use my chair for this, asking like a follow-on question. Do you know if more detections or higher SNR detections would be better?
Oh, that's a good question too. I'm not quite sure what the number would be. From what I've heard before, it's at least a couple hundred, but I should also note that these models are always being improved, and these models may not be modeling perfectly or as well as it could, the pulsational pair instability supernova physics, as well as the broken power law. So I don't know the numbers off the top of my head. I can look it up and let you know, but in terms of SNR versus, what was it again? SNR versus number of events, I imagine both will help, but I imagine with 04 and 03B, we'll have many more events, and maybe that will be first before very large SNR events. Great.
Let's thank Shanika again.
Thanks.
And as a reminder, our second speaker had to cancel, so we're moving everything up a block. So up next, we have Oliver Anagnostou, who will be talking about hierarchical formation of intermediate mass black holes. Thank you.
All right, hi guys. So if you don't know me, my name is Oliver, and I'm a PhD student here at the University of Melbourne under the supervision of Andrew Millhouse and Michele Trenti. And as stated, today I want to talk to you briefly about the hierarchical formation of black holes and some of the problems that arise when trying to consider such formation. So first of all, the problem that leads to us to want to think about these hierarchical formation scenarios, as many of you have already heard about this week and probably prior, is the GW190521 detection that was announced last year. So it was a detection of a binary black hole merger involving a 85 solar mass black hole merging with a 66 solar mass black hole, which led to the formation of an approximately 142 solar mass IMBH. And the reason why this was particularly interesting, at least for me, is that these progenitors are challenging to explain with the standard models of stellar evolution. And that's because of what's known as the upper black hole mass gap, which we so kindly just heard about. So it's due to the pair instability supernova that leads to a theoretical cutoff of around 50 solar masses. And this basically means that at least the primary N1 is well within this mass gap. So basically, we don't really think that it is formed through direct stellar collapse. So essentially, it's too heavy. What do we know? So we want to try and work out how can we form such a heavy primary. And that's where hierarchical mergers come in as a potential solution. So you've already heard a bit about this, but I'll just give a brief overview again. So hierarchical mergers are when you have successive black hole binary mergers in the course of dense star clusters, such as globule clusters. The basic process is you form your regular stellar black holes, and they quickly migrate to the center of the cluster due to dynamical friction. And then you form this dense inner core of compact bodies that lead to binary formation. And then again, due to these high densities, you get a lot of like close encounters, which can lead to things like three-body hardening and dynamical exchanges, the result of which means that you can get quite rapid mergers of binaries, a lot more rapid than you would get just purely from gravitational wave emission. So the result is then you can get these second generation black holes, the ones formed through the merger of stellar black holes, that can be heavier than is allowed through regular stellar evolution. And then if they're retained, they can go on to merge again, to form third generation black holes, and so on and so on. However, the main issue there is that you need to be able to retain the black holes that are produced through these mergers. So that brings me to what I'd like to affectionately call Snowball, which, so basically we had a set of 58 simulations, n-body simulations of globule clusters. And in one specific simulation, we found a chain of 7 black hole binary mergers, which led to a final mass of about 97.8 solar masses. And we estimate the rate of this, a merger such as this, of forming an 8th generation black hole to be 0.03 per gigaparsec cubed per year, which is within the 90% confidence interval of the inferred rate of events similar to GW190521. And as I said, we did 58 n-body simulations, and we weren't specifically looking for this, but what we realized is we could take the set of all merger chains that we found in these simulations and try and look at the statistics. So you see, okay, you can't see my mouse, but basically on the left there, you have the one with chain length 7, where chain length is essentially just the number of binary mergers that lead to the final black hole. But you'll also see there that there's 3 columns: no recoil, recoil with no spin, and recoil with spin. And this comes down to what I was talking about earlier about black hole retention. So this is a bit of a problem, because we need to talk about gravitational recoil, which is a bit of a thorn in my side, unfortunately, because gravitational recoil is a velocity kick imparted onto a merger product due to the asymmetric emission of gravitational waves. That essentially leads to some net linear momentum flux, which can basically launch the second generation black hole out of the cluster, meaning it can no longer go on to merge again. The emission asymmetry basically comes from any asymmetry in the binary, whether that be unequal masses or spins. And you can do a little back of the envelope calculation to show that essentially this recoil velocity depends on X, meaning the percentage mass loss or percentage of black hole mass converted into gravitational waves, and beta, which is essentially how directional or how asymmetric the emissions is. But in order to actually do the proper calculations, you need numerical relativity, which is hard. So some people that are a lot smarter than me have managed to derive analytic approximations fitted using numerical relativity. And I'm going to break the cardinal sin of any talk and have some big ugly equations, mainly to show you how big and ugly these equations are. But also, I just want to quickly point out that essentially it depends on the mass ratio of the binary, not the actual masses of the black holes themselves, just the mass ratio, and also the spin magnitudes and directions. And the problem here, as I said, they're big and ugly. So it makes calculating these recoil velocities quite hard. In order to get a bit of an understanding of it, I can show you this plot here, which on the horizontal axis, you've got the mass ratio, and on the vertical, the spin magnitudes. And it also depends on the spin directions, or more specifically, the orientations of the 2 spins with respect to each other and the orbital angular momentum. So basically what I did here is for each data point, I've averaged over 1,000 different spin orientations where the spins of the 2 black holes are just drawn isotropically. And the most important takeaway from this plot is you'll see that the highest velocities you get tend to be around a mass ratio of 0.4. And this is a bit of a problem because if we then try and calculate these, so just a caveat that for the simulations we did, gravitational recoil aren't calculated within the simulations. We have to calculate after the fact. But if we do that, we only get 33% retention of these second generation black holes, the ones formed through a merger. And indeed, Snowball, the one that formed from the 7 mergers, is now ejected after the second merger. So we no longer get this 97 solar mass black hole, unfortunately. And only one chain of length 3 is remaining. And the main reason is because of what I showed on the previous slide, that once you have a second generation black hole, it's going to be more massive than the black holes that can form through stellar collapse, which means any subsequent merger it has is going to have a lower mass ratio and get close to around that 0.4, which basically means that like the recoil velocities are going to be high enough to pretty much always guarantee ejection from the cluster. So then, as I said here, no third generation black holes are retained. So can we still produce IMBHs if we have this new, the gravitational recoil? Well, sort of. You just have to have a very specific set of circumstances. So this is a potential formation pathway for GW190521, assuming that both the both the primary and secondary black holes are indeed not formed through stellar collapse. So you can have this scenario where both the primary and secondary are second generation black holes. And you can find an area parameter space that shows the consistent progenitor spins and mass loss to produce the final 142 solar mass black hole, and also have sufficiently low gravitational recoils that they would be retained within reasonable, like regular globular clusters, assuming that it was formed within a globular cluster. So basically, yes, you still can form things like GW190521 through hierarchical mergers. It just, you have to have very fine-tuned initial masses and spin combinations to make sure that the progenitors aren't ejected before they can ever form a binary and merge. So just to summarize and talk about the future, you can use hierarchical mergers to form black holes within the upper black hole mass gap. It's just hard to then retain such black holes within binaries. But it's still a consistent pathway to form GW190521. But what I want to do in the future is include calculations of gravitational recoil on the bat in hopefully the new PETA code, which is a new n-body code, which is quite a lot more efficient than the n-body code I've been using, which will hopefully allow for much larger simulations of hopefully around 1 million bodies, so realistically sized globular clusters with recoil calculated on the fly, so that we can hopefully better study these hierarchical mergers within dense star clusters, and then hopefully compare to 03 and 04 and so on. Thank you.
All right, thank you, Oliver. So there are a few questions in the chat. Make sure I get the first one. The first one is from Balu. When you talk about the mergers in the globular clusters, are you talking about the collision rates? If so, what is the typical collision rate in a cluster?
So the first thing I want to mention is when we talk about things like collisions in globular clusters, sometimes that just means close encounters. So they call it a collisional system just because you can get these encounters where they affect each other's, like basically they come within each other's gravitational field close enough to be diverted. The collision rates can actually be quite high. So for any typical black hole within the center of like an approximately 100,000 star system, you could get like hundreds of essentially close encounters within like 100 mega years essentially, but it's highly dependent on the specific densities of the cluster though.
And the next question from Gary DaCosta. What are your globular cluster? Oh, sorry, I skipped one. This one's from Alessandro Paduano. Is there a specific globular cluster in the galaxy that would be the best candidate to search for an IMBH formed through hierarchical mergers? Would it need to be a high density 4-mass cluster?
Yeah, so basically, the higher the mass of the cluster, the more ideal it would be to form an IMBH, just because the escape velocity is higher, which means you're more likely to retain these second generation black holes. So something like Omega Centauri or 47 Tuc, probably the two ideal candidates, just because they're both very massive and quite dense. But again, it's it would be very difficult to be able to see that, because in the center of the clusters, you're not going to get much accretion, because basically it only has black holes. So I don't know how you'd really see it, unfortunately.
We've got time for one more question. So this is a question from Gary DaCosta. What are your globular cluster masses? How massive a star cluster needs? How massive does a star cluster need to be to retain a higher fraction of black holes?
That's a good question. So the cluster masses for ours, at least at the start of their 12 gigayear evolution, is around 5 by 10 to the 4 to about 10 to the 5 solar masses. But we have a whole range of different masses. So I don't have I don't have it here, but I'd encourage you to look me up on archive and read some of our papers to see. Ideally, you'd want to have at least upwards of 5 by 10 to the 5 solar masses to help retain higher amounts of these second generation black holes. But again, no one's really able to do those sort of simulations yet with calculations of gravitational recoil. So I can't really speak on it yet, but that's hopefully what I want to do in the near future.
Okay, thank you. And there are more questions on Slack, so hopefully we can continue discussion there. Let's thank Oliver again. And then for our next talk, we'll hear about supernovae from Jade. So Jade Powell will be giving a talk titled Gravitational Waves from 3D Simulations of Supernovae, including rotation and magnetic fields. So go ahead, Jade.
Hello. Hopefully that microphone's okay. Yeah, so I'm Jade Powell. I'm from Swindon, and I'm going to talk about supernovae and gravitational waves. So gravitational waves have been detected from lots of binary black holes and neutron stars, as you've already heard lots of times today. And we detected about 60 so far, and we're expecting to detect a bunch more during 04. But we might also start to detect other things as the detectors are becoming more sensitive. And I hope that one of those things will be a core collapse supernova signal. So core collapse supernovae would be a perfect multi-messenger source, because we see loads of supernovae all the time electromagnetically, and but the signal you get in EM comes from the outer regions of the explosion, and light can escape from the inner regions. And so to learn about the inner regions of the explosion, you need gravitational waves or neutrinos to learn about those things. But we've only had one neutrino signal so far from the supernova and no gravitational waves, because you can only detect them out to much smaller distances than you can the electromagnetic radiation. So when a supernova explodes, there's the core bounce, and then a shock wave is launched outwards. But the shock wave in a supernova doesn't have enough energy to fully explode, and then it just stops moving outwards. And then it has to get some energy from somewhere to power a full supernova explosion. And so the way we think this happens for most standard supernovae is that they absorb a bunch of the energy from the neutrinos that are emitted, and that repowers the shock wave, and you get a full explosion. And so to understand gravitational wave signals from supernovae, you have to do 3D simulations. They take like a good few months just to do like 1 second of one supernova signal. And so the majority of these simulations so far in 3D have been for regular mass supernovae, and by that I mean between say 12 and 20 zero-inch main sequence mass, and they have this neutrino-driven explosion mechanism, and we don't include rotation, and we don't include magnetic fields. And because we have quite a few of these type of simulations now, we've started to learn some things about the gravitational wave signal from these typical supernovae. So I have here the time series of a gravitational wave signal from a regular supernova, and also the spectrogram. And so we don't usually use the time series for supernova searches and parameter estimation for gravitational waves because they have a lot of stochastic features which we can't relate back to the source properties. However, when you look in the time frequency spectrogram, then we see some features which are related to the source properties that are common between all supernova simulations. So we have this, don't know if you can see the mouse. Oh yes, you can. So you have this like high frequency mode here, which rises in frequency with time as the mass increases and the radius of the proton-neutron star gets smaller. And and then it has this peak amplitude, which usually occurs just after the shock is revived. And then it has smaller, like little bits of amplitude along the mode. And you can't predict where the little second peaks of amplitude will be. Like we can predict this shape, this rising time of frequency, but we can't predict all the little fluctuations in amplitude. That's the stochastic part, which causes all these like little spikes in the time series. And then we also have some lower frequency modes here, which are related to the shock radius and also the radius of the proton-neutron star. So you can see in this one, the frequency of the gravitational wave increases with time. This is the point where the star explodes, and then the shock radius, because this depends on the shock radius, the frequency just dies out and the amplitude of this higher frequency mode reaches its peak. So we can't really tell much about what's going on in the inner regions of the star from the time series, but we can tell quite a few things from the spectrogram. And this deviation from zero in the time series is caused by the gravitational wave memory from the mass motions, but it occurs at frequencies that's too low for current gravitational wave detectors, so you wouldn't be able to see that anyway. And there's also a low frequency component from the neutrinos, but I haven't actually calculated that for any of my models before. So now that we have a good idea of how things work for supernova signals for regular garden variety supernovae, we need to know how what to expect for signals that have rotation. There are some good 3D supernova simulations available that include magnetic fields and rotation, but most of them don't include the gravitational wave emission at all. And some of the ones that do include the gravitational wave emission, they only simulate for the first 40 milliseconds around when the core bounces, like this one here from this 2008 paper. But the actual signal should be like maybe even several seconds long. So you can't really do your gravitational wave data analysis when you just have the first 40 seconds of your signal and not the rest of it. So, but we do understand that at this core bounce time that you get this big spike in the gravitational wave time series, and the size of that spike is related to the rotation rate. So the more rapidly you rotate, the bigger the spike you get. But we didn't know what would happen for the rest of the gravitational wave signal in this case. And some of these ones that the short simulations that include magnetic fields and rotation, they also have some other issues, like they're only in 2D, and if you do a 2D supernova simulation, you only get one out of the two polarizations that you get in a gravitational wave signal. And they have problems like equations of state that don't match observations anymore, and things like that. So what we want to do now is to do lots of simulations, including rotation and magnetic fields. So the first one that we did was a 39 solar mass model, where it's a 39 solar mass helium star, where we included rapid rotation, but no magnetic fields. And that's published in this paper. I put the archive link. And so this is what the gravitational wave signal looked like. this is only the plus polarization, and this is as seen emitted from the equator of the star and here at the pole. And so you can see here it had this big spike of core bounce time like we saw in the previous one where they only did 40 milliseconds. Then we also calculated all of this signal here that comes after that time. And so if we saw that it has a similar rise in frequency with time as with the neutrino-driven supernovae. But one thing that we found that was different, that the equation that I showed previously that relates the frequency of this gravitational wave emission to the mass and radius of the proto-neutron star doesn't work anymore for this model. So the relationship between the gravitational wave frequency and the mass and the radius breaks down once you include rapid rotation. And so I also calculated the detection distances for this model in the LIGO, Virgo, Cagra, and two different possible designs for a future detector called Einstein telescope. So you can detect these models out to a few hundred kiloparsecs in current detectors, but up to megaparsec distances with Einstein telescope. So next we want to include magnetic fields as well as rotation. And the first step to doing this was to do it in 2D. So we have this paper by Ryland Jade, who was an honors student at Monash, and he did 16 two-dimensional simulations with a variety of rotation rates and magnetic field strengths using a 15 solar mass model and a 39 solar mass model. And so I've just pulled out one of his gravitational wave signals as an example. And so here's the time series, and here's the time frequency. And you can see again that it has this rise in frequency in time. And the black line is the gravitational wave frequency as predicted by the equation that I showed earlier. And it's a reasonably good fit, except for at late times, even though my 3D model with rotation didn't really obey that line. And so one thing that I thought was interesting was that because the previous simulations with rotation and magnetic fields were only 40 milliseconds, they were stopped before the star actually exploded. And so we didn't know which ones exploded by the neutrino-driven mechanism and which ones exploded by what we call the magnetorotational mechanism, where the explosion is powered by the energy from the magnetic fields and the rotation instead of by the neutrinos. And so we found out in these 2D models that only the ones with the most extreme magnetic fields and rotations actually exploded by the magnetorotational mechanism, and the rest of them were still neutrino-driven explosions. And so we also thought that the models with the highest magnetic fields and rotation would have the strongest gravitational wave emission. But in Ryland's paper of 2D models, we found that wasn't always the case. So here we have, this is the amplitude spectral density of the gravitational wave signals. This is the amplitude, and this is the frequency. And these colored lines here are the gravitational wave detectors. So it shows like this is the frequency and the amplitude at which these detectors can detect gravitational waves. And then this is our supernova signals. And so the one with the most extreme magnetic fields and rotation is this green one. And you can see that these orange and blue lines, which have not so strong magnetic fields, actually have higher gravitational wave amplitudes than the green line. So yeah, I thought that was also interesting. So now that we've done some 2D simulations with magnetic fields and rotation, now what I'm doing is 3D simulations with magnetic fields and rotation. So we've done a smaller number of these because they take a much more computer power and a longer time. So I've done the 39 solar mass model in 3D with two different magnetic field strengths of 10 to the power of 10 Gauss and 10 to the power of 12. And so this is work that's still in progress. And, yeah, still working on the results. So how long have I got, Meg? Oh, crap. I gone too long. Okay, so let me just skip. So the models have really big jets, and you can see that this model with the lower magnetic field has a more powerful jet than one with the higher magnetic field. So I thought that was something interesting about these new models. And this is what the gravitational wave signals look like. They're a bit higher frequency than the ones I showed earlier, but overall have the same shape. And this is how far you can detect them out in current LIGO detectors and some future proposed detectors, Einstein Telescope and Cosmic Explorer. But these are like a lower limit on detection distance because we only include a small part of the total gravitational wave signal still, even though hours are longer than the others. And also because we don't include general relativity yet in the code that has magnetic fields, it also makes the gravitational wave frequency a little higher than it should be. And so that takes it out of the, it makes the sensitivity of the detector a little worse if you go to higher frequencies. So I think that would also help us get larger detector distances. Okay, sorry I went too long.
I have time for one question.
Okay.
So first question was from Reinhold, who asks whether the current lack of supernova detections in gravitational waves provides a useful upper limit on the number of newly formed black holes in the local region, which may have very dim supernova likelihood.
So we do have upper limits on some extreme supernova models, but we haven't tried to use a non-detection for upper limits on anything else yet.
I think we're out of time. There are a couple more questions in the Slack
Okay,
channel.
I'll answer on that.
Okay, so next up we have Paul Easter. Let me double check. Yes, we have Paul Easter. Are you online, Paul?
I am. Can you hear me, Meg?
Yes, so go ahead and share your screen if you want.
Cool.
And Paul will be giving a talk about detecting binary neutron star post-merger remnants and measuring when they collapse. So I'll ping you in the chat and you have 2 minutes. Thank you. You can go ahead and share your screen. If that works. I'll let text.
Does that work? Is that working?
Yes, it's working.
Cool. Yeah, hi everyone. I'm Paul Easter. I'm just finishing off my PhD at Monash University. I've been looking into probing extreme matter with gravitational waves from binary neutron star mergers, and I've been working with Paul Waskey and Andy Casey. And my arrow keys aren't working. It's all right. Okay. So how extreme are post-merger remnants from binary neutron star mergers? So before I answer that, I have a phase diagram here of the universe, the matter in the universe, and it's in relation to temperature versus density. But before I continue on, I'm going to highlight the scale of the units that are on both axes. The temperature is in gigakelvin, and the density is in units of nuclear density. So we're talking about extremely high temperatures and extremely high densities. So the majority of matter in the universe is essentially sitting at the origin. I'm not sure whether you can see my mouse here. Yeah, so most of the matter here is sitting in the origin of this plot. But the man-made particle accelerators can probe the parts of the parameter space shown here. So they can probe up to nuclear density at quite high temperatures. Conversely, the part of the phase space that the early universe sits in is low density but very high temperatures. So the obvious question from that is, where do neutron stars sit? And this is where they sit roughly. This is all approximate. So there's several times the density of nuclear matter, but also in this plot, in this picture especially, they're very low temperature as well, which is quite strange because Neutron stars, of course, aren't low temperature. Astronomically, they're quite high temperature. They have high temperature, but in this scale, they don't. However, when neutron stars merge, and if they do not collapse to form a black hole, then the post-merger remnant that forms is both very hot and both very dense. So it really is a real extreme form of matter. Probably, you know, one of the most extreme forms of matter in that part of the parameter space. So how do these things form? So we'll look a bit into the binary neutron star evolution. Of course, this is a 12-minute talk, so unfortunately I won't be able to go into great detail on anything, so feel free to ping me on any questions that you want. But we start with panel A. We have the in-spiraling neutron stars. If they're close enough together, eventually through emission of gravitational waves, they'll merge together in panel B. And depending on the mass of the system, this will either collapse into a black hole or form a post-merger remnant, which I've highlighted here. And this post-merger remnant is supported against collapse into a black hole because it's differentially rotating. And this post-merger remnant can either evolve into a black hole or originally rotating magnetar or a stable neutron star, depending on the mass of the system. And the time scale for this is in the order of milliseconds to seconds. So here's a simulation of a binary neutron star merger. The gravitational waves are shown down the bottom and the time is on the top right. I hope this comes out all right on Slack. So it's in spiraling now. The gravitational wave signal is chirping up, and when it merges, the differentially rotating remnant emits gravitational waves at a much higher frequency. And then it collapses into a black hole in this particular simulation. So let's have a little bit of a look into the gravitational waves for these post-merger remnants. So on the left, I've got a gravitational wave strain, similar to what you saw on the previous plot, generated by numerical relativity simulation that Jade was talking a lot about previously, which was a good segue for me. And on the right-hand side is the spectra for the post-merger part of the gravitational wave strain. These waveforms are generated with numerical relativity simulations, and these simulations are extremely expensive. They're very time consuming. To be able to simulate these post-merger remnants, especially in the first place, a lot of compromises need to be made just to keep the simulation time practical. And Jade actually mentioned a lot of those compromises, but the offshoot of that is we're not 100%, well, we're not certain, I won't even say 100%, we're not certain that there's going to be a great correlation between the gravitational wave signal from numerical relativity simulations and what appears in nature. So there's a little bit of uncertainty there. So any models that we develop need to sort of take that consideration into account. And also, we need models because we need to be able to generate waveforms quickly. That this is a good point where Bayes-wave being unmodeled is able to do this. But here we're not talking about unmodeled things, we're talking about modeled things. So we'll talk about the analytical model that I developed for post-merger gravitational waves. Here we ended up using Dobie, the Bayesian inference package that was developed in Monash with collaborators. And we're using this model here that I'm showing up the top left-hand side. It's the simplest model that I could come up with that would give us a good fit. And it's informed by the post-merger literature, in that a lot of the, or some of the spectrographs that were shown for the post-merger remnant showed drifts in the frequency domain. So this is a third order exponentially damped sinusoid with a frequency drift term. The left-hand side, I'm showing both, the left-hand panel, I'm showing both the time domain and the frequency domain for the gravitational wave signal. The gravitational wave ejection is shown in the black curves, and the posterior waveforms that we recover are shown in the shaded coloured curves, both in the time and frequency domain. And at least visually, you can see that we fit both the time and the frequency well. But it's not just visually. We calculated the fits, noise-weighted fitting factors, and we found that we were able to fit the waveforms quite well with 90% plus fitting factors. And we're able to detect post-merger signal-to-noise ratios of 7 and above. And with this model, we're also able to probe the hot equation of state by looking at the peak, the frequency of the dominant post-merger oscillation frequency for the remnant. And our results are shown in blue, and as a comparison that we did in our paper, we used phase wave as well, and that's shown in brown. So what about the equation of state? For this, we used a different model. We used a hierarchical model, if you like, you can call it machine learning model, that was trained on the spectra for numerical relativity simulations and neutron star parameters, progenitor parameters. We only had 35 numerical relativity simulations, and we did our fits by using leave one out cross validation, if that means anything to anyone. And we ended up getting fits of around 88%. The top left shows the injected numerical relativity spectra in black dashed curves, and our fit is shown in red with errors, with uncertainties, I should say. This model is also bidirectional, so that we're able to, given the progenitor neutron star properties, in this case the mass and the tidal parameter, we're able to generate spectra, which we're showing on the bottom left. And on the bottom right, we're showing that we can, given the spectra, we can infer the tidal parameters, which is on the bottom right. So the other thing we wanted to be able to look at is extending the model so that we could measure the collapse time of the binary neutron star merger. And I see I'm starting to run out of time here. So again, the numerical relativity simulation is shown in black, the black curve on the top left. The collapse time injection is shown by the solid vertical black line. And the collapse time posteriors that we recovered is shown in the shaded blue region on the left-hand side. On the right-hand side is our posteriors that we recovered. So for the 10 millisecond injection, we recovered our posteriors quite well. So we did this with a 4-detector network. We found that with 2A plus 10 millisecond collapse time injection, the event needs to occur at 8 megaparsecs, which is close. For a GW190817-like event at 40 megaparsecs, for a 10 millisecond collapse time, we found that we need either an Einstein telescope or Einstein telescope with Cosmic Explorer network required. And that's it, thank you. Well, maybe I shouldn't stop sharing yet.
Thank you, Paul. So I don't believe we have any questions on Slack yet. I'll ask a question though. So in the earlier sort of model you showed where you modeled post-merger, I think you said it was a damped sinusoid with, oh, sorry, I'm not using the mic. Sorry. When you used, I think it was a damped sinusoid of frequency drift. Is that correct?
Yes.
So was that basically just trying to pick out the main sort of F peak, or was that trying to fit multiple features of the post-merger waveform?
The dominant, the first mode, if you like, or the first order picks out the dominant peak, but the other two, second and third order sinusoids are designed to sort of capture the more complex nature of the post-merger gravitational wave signal. Okay,
great. And did you, like, including the sort of subdominant peaks, does it make a big difference, or are they still sort of, you know?
It does make a fairly big difference on the fitting factors. I haven't got the actual numbers, but qualitatively adding in the extra degrees helped a lot. It sounds very similar to a base wave question because you could easily, well not easily, but you could use evidence to determine how many orders you wanted for this, I guess, as well.
Okay, great, thank you. Yeah, and if anyone has any questions later, please feel free to pop them in the chat. Thank you again, Paul.
Cool.
And so for our next talk, we have Dougal Dobie, who I believe should also be online.
Yep.
Great, yes, we can see you and we can hear you. Go ahead and share your screen.
You got my screen now?
It still says started shares. There we go, perfect.
Perfect.
Right. So Dougal will be giving us a talk about a comprehensive search for the radio counterpart of GW190814. So take it away.
Thank you. So as Meg said, I'm Dougal Dobie. I'm an Ausgrave postdoctoral research fellow at Swinburne, and today I'll be talking about the ongoing follow-up of GW190814 that I've been leading for the past 2 years with the Australian Square Kilometre Array Pathfinder. So the speakers before me have introduced some of the results from the third LIGO observing run, and you'll hear more about them over the next 2 days as well. So I'm not going to spend any time on that, but I will give you a bit of an introduction to this source in particular. So GW190814 was initially localized to 23 square degrees, and that's since improved to 18. The merger was first classified as a mass gap event, which I'll come back to on the next slide, before being revised down to a neutron star black hole merger, and then revised again to a mass gap event. And the distance to this merger was roughly 240 megaparsecs, which is much further than GW170817. And unlike GW170817, there was no coincident GRB detected. So what is a mass gap event? This plot shows the masses of the various compact objects in the universe that have been detected, as we saw in the first talk. But the difference between this plot and the previous plot was that this one has the components of GW190814 and the resulting object highlighted. And as you can see, the lighter component falls somewhere in between the population of known neutron stars and known black holes. So with a mass of 2.6 solar masses, it's either the heaviest neutron star ever detected or the lightest black hole. And with current gravitational wave detectors, there's no way to actually determine the physical nature of the merger components. You basically just infer them based on the mass, although that may change with next generation detectors. Now, that being said, the detection of an electromagnetic counterpart would, at least in my mind, fairly conclusively show you that the lighter component was in fact a neutron star. So it makes sense that we should dedicate some amount of observing time to following up this event and searching for that counterpart. So that's what we did. We used ASCAP, which is capable of rapidly observing vast swathes of sky. And this event was so well localized that we only needed a single 30 square degree pointing to achieve fairly good coverage of the event. This plot on the right shows our first image of the field taken a few days post-merger. We have a 35 microjansky RMS sensitivity, and in the dashed and solid lines, I've overlaid the 50 and 90% sky map contours respectively. So the red contour shows the initial localization, which we got pretty much right after the merger. That's what we use to calculate our pointing and everything like that. The blue shows the final localization from the full parameter estimates. It was released months after that. You can see it's shrunk a little bit. It's shifted a little bit as well, but overall, it doesn't really change any of the takeaways from this work. So we've now hit this field 10 times on roughly a logarithmic cadence, and that's just basically motivated by the fact that synchrotron afterglows generally evolve on logarithmic timescales. So after 3 epochs, going out to a month post-merger, we published a paper claiming a non-detection and used that non-detection to constrain the properties of the merger, basically just by comparing our upper limits to the properties of afterglow light curve models and typical short GRBs. And our results weren't overly constraining, but we were able to rule out the merger as being on axis. So the plot there shows the shaded region is the parameter space that we can rule out. So we basically say it wasn't less than 10 degrees fairly comprehensively. The gravitational wave data, again, full parameter estimates released months after this, suggest that the merger inclination angle was about 45 degrees. So our results are in fairly good agreement. Now, when I've given this kind of talk previously over the past year or so, I've had people fairly regularly ask sort of why bother keep to look despite not finding anything in that first month. You know, why spend so much observing time on this one event? And in short, the answer is that we don't really understand what to expect from these kinds of events. Even if you assume that all of them are like 170817, which is probably the most well-studied astronomical object in the past couple of decades, there's still a ton of debate as to things like the exact structure of the merger jet, the outflow, how that those two interacted, and all sorts of things like that. And on top of that, just for relativistic transients in general, we don't really have a great understanding of the typical microphysics parameters. One of the goals of electromagnetic follow-up is to improve our understanding of all of these, which pretty much means we can't bias our searches by assuming that every event is going to be GW170817 like. We need to sort of probe the full parameter space, and that means observing from almost immediately after the merger out to months or years post-merger. Now, the other important factor for this event in particular is that the larger the merger inclination angle is, the later the light curve will peak. And so even if GW170817 is typical for these kinds of events, if we'd observed that event 45 degrees off axis, as opposed to sort of the 10 or 20 that it was, it wouldn't have peaked for hundreds of days post-merger. And so even if GW170817 is perfectly canonical, we still need to be observing for those months to years. So we did that, carried out those observations, and after applying a series of quantitative and qualitative cuts to all 70,000 sources that we found in our imaging, I was able to narrow our search down to 12 candidate counterparts just based on the light curve structure and the images themselves as well. Now we can immediately rule out 8 of these as they're spatially inconsistent with the gravitational wave event at over 99% confidence. And 3 of the remaining ones aren't very variable. They've got modulation indices of around sort of 20, 25, 30% or so. And in comparison, a compact extragalactic radio source that is, persistent and in a steady state in this patch of sky is going to be varying by about 30% due to refractive scintillation. And so we can't comprehensively rule these sources out as being the counterpart, but based on the balance of probability, it's overall fairly unlikely that they're related. Now that leaves one source that has a modulation index of 90%. It's spatially consistent with the merger, and in addition, which wasn't a defining feature, but it is nice nonetheless, it has multiple constraining non-detections in the early observations. So it exhibits an extremely rapid rise. It triples in flux between 234 and 260 days post-merger. And unfortunately, even under the most extreme assumptions, where you take an extremely energetic top hat jet that's very off-axis, it's propagating to an extremely dense medium, you still can't reproduce the rapid rise that we see at such late times. And so we ultimately conclude that this source is unrelated to 1908-14, but unlike the other 11 sources, this one is likely to be real astronomical transient. It just occurred something like 6-ish months after 1908-14. Now, we've got ongoing follow-up programs across the entire electromagnetic spectrum to try and determine what this thing is. All that work is still ongoing, and I hope I can present it all to you in person at next year's ASA. So ultimately, we found no counterparts to this event. And again, we can do what we did in the first paper. We used that to place constraints on the inclination angle and circummerger density. So this plot's slightly different. I've got the properties of a Gaussian jet on the left and a top hat jet on the right. And basically, we can rule out the parameter space to the upper left of the hatched regions there, with the width of those regions just corresponding to the uncertainty in the distance estimates to the merger. So we can now fairly comprehensively rule out the observing angles less than 20 degrees, or alternatively, if you take the gravitational wave data and you know that this was about 45 degrees off axis, we're now starting to push into the typical GRB circummerger densities of a few parts in 100. So we're not fully ruling out the possibility that there was a jet launched by this merger, but we're definitely starting to place much tighter constraints than we were previously. So I've got a little bit of time left, and I'd just like to use my final 2 slides today to show the utility of these observations. So the top panel here shows the light curve and spectral energy distribution of a candidate counterpart discovered by a competing group using the VLA rather than ASCAP. And ultimately, they rule it out on physical grounds. So just that, like we did for our counterpart, the merger parameters required to produce that kind of afterglow are just unlikely. However, the difference between their candidate and our candidate is that our candidate can't be produced even using parameters that are like 3 orders of magnitude larger than typical values. It's just beyond the realms of possibility, really. Whereas for this candidate, the parameters of the sort for the energetics and things like that, they're high, but they're not unbelievably so. Like, it's reasonable to rule this source out, but it's within the realms of possibility that it could be the counterpart. Now, that's where ASCAP comes in. Our wide field follow-up events like this means we pretty much just get coverage of every candidate for free. We don't have to do any sort of dedicated follow-up. We just have them all in our field of view as is. And our observations for this source show that it's actually not variable at all. We can comprehensively rule out independent of any sort of physical arguments. It's just the reality is it's not actually variable. And this kind of work is going to be really important over the coming decades as we move to the next generation of gravitational wave detectors, where they'll be detecting, hundreds, if not thousands of mergers per year, and dedicated follow-up of every single event. It's not going to be possible. And this serendipitous coverage is really where we're going to be able to place useful constraints on these sources. So on a slightly different note, I'd just like to point out some of the serendipitous science that's been done with these observations. They're really a unique opportunity. We've made each of these observations public pretty much as soon as they pass our internal validation checks, just to make sure everything's sane. And these observations are one of the richest radio data sets that we have. We've got huge sky coverage, we've got a large number of epochs, a long time baseline, they're sensitive, we've got full polarization, the list just goes on and on and on. Pretty much anything you could ask for in the radio continuum, we have here. And so there's 2 other papers that have used this data. One comes from a group of people in the EMU collaboration that they basically stack all 10 epochs to get the most sensitive ASCAP observation to date. And they find this odd radio circle. And the other, led by Yuanming Wang, who's a PhD student in Sydney, found a series of rapid scintillators that suggest that there's a long plasma filament in our galaxy sort of passing straight through the middle of this field. Now, I just cannot stress enough how much unique science there is that can be found in this data set, and also how little time I actually have to explore it myself. So I'd really thoroughly encourage anyone who has any interest in the radio continuum to have a look at this data. It's all on CASDA, and just see what they can do with it. And so I'll leave you with my concluding slides. Thank you.
Great, thank you so much, Dougal. So we have one question in the chat from Patrick Armstrong. So at what point can you say we've been searching for this long enough, it's probably a black hole?
I guess it depends on how confident you want to be. I would say not quantitatively or anything, but my gut feeling is that it probably is a black hole based on our non-detection. Unfortunately, our observations just aren't sensitive enough to be like completely comprehensive. But like I said, we are sort of starting to push into that regime where we can begin to rule out some fraction of the typical GRB parameter space.
Great, thank you. And then there's a question from Thomas Nordlander. Thanks for the great talk. Any point to doing an optical follow-up of your mystery false counterpart object?
Yeah, so we had a night with Keck that was not weathered out, but the seeing was so poor that we just couldn't do anything useful. Unfortunately, this source is offset by a very small amount from an unrelated M dwarf, so you kind of need extremely good seeing. But we've got Gemini observations coming up in the next semester, so hopefully that'll be useful.
Okay, great, thank you. And there's one more question, which is a fast one. What RA and DEC are your follow-ups centered on?
It's roughly 1 hour and minus 23 degrees in DEC, off the top of my head.
Okay, thank you. And that was from Kat Ross. Sorry, I forgot to mention that. Okay, great, thank you. And remember, you can use Slack for any other follow-up discussion. Yeah, so that is the end of our session today. We're ending early because we missed a talk. Let's thank our speakers again. We had really great talks. Yeah, thank you.